Imagine for a moment that everything you know, everything that exists, every atom, every galaxy, every thought you've ever had, could vanish in less than a heartbeat. Not through some cosmic collision or the gradual heat death that scientists have long predicted will claim our universe billions of years from now, but in an instant so sudden, so absolute, that you wouldn't even have time to realize it was happening. There would be no warning, no alarm bells, no chance for goodbye. One moment, existence. The next, nothing. Complete and utter annihilation traveling at the speed of light. A wave of destruction so perfect that even the laws of physics themselves would be rewritten in its wake. This isn't science fiction. This isn't some doomsday prophet's fevered imagination. This is a genuine possibility sitting at the heart of our most fundamental understanding of reality, and it has a name that sounds almost mundane for something so terrifying: vacuum decay. Right now, as you listen to these words, you're surrounded by what most people would call empty space. But here's something that might unsettle you. That emptiness isn't actually empty at all. The vacuum of space, that vast nothingness between stars and galaxies, is teeming with energy, humming with quantum fields that permeate every corner of existence. These fields are like invisible oceans in which we're all submerged, so fundamental to reality that we can't perceive them directly. Yet they determine the very nature of matter, energy, and the forces that bind the universe together. Among these fields is something called the Higgs field, and it's this field that might hold the key to our universe's ultimate fate. Here's the unsettling part. There's a possibility, a very real possibility according to our best scientific understanding, that the Higgs field is in what physicists call a false vacuum state. Think of it like a ball sitting in a shallow valley on the side of a mountain. It looks stable, seems stable, has been stable for nearly 14 billion years, but it's not in the lowest possible energy state. Somewhere down below, there's a deeper valley, a true vacuum, and if that ball ever rolls down to it, everything changes. Ask yourself this question. How do you know that the ground beneath your feet is truly solid, that the reality you experience isn't just a temporary configuration of energy waiting to collapse into something else entirely? It's a disturbing thought, isn't it? The notion that the stability of existence itself might be an illusion, a cosmic accident that's persisted only because the universe hasn't yet stumbled upon its true ground state. This is the essence of the vacuum decay scenario, and before you dismiss it as theoretical speculation too distant to matter, consider this. Measurements taken at the Large Hadron Collider, the most powerful particle accelerator ever built, have revealed something troubling. The mass of the Higgs boson, discovered in 2012 after a search lasting decades, combined with the mass of another particle called the top quark, places our universe right on the knife's edge between stability and metastability. We're living, potentially, in what physicists call a metastable universe, one that could persist for trillions upon trillions of years or could, theoretically, end at any moment. Let me paint you a picture of what vacuum decay would actually look like, though "look like" is perhaps the wrong phrase since there would be no one left to observe it. Somewhere in the universe, through a process called quantum tunneling, a tiny bubble of true vacuum would spontaneously form. This could happen anywhere. In the depths of intergalactic space, in the heart of a distant star, perhaps even right here in our own galaxy. The location wouldn't matter because what happens next is inevitable and unstoppable. That bubble would begin to expand at the speed of light. Its boundary a wall of destruction beyond which the laws of physics as we know them simply cease to apply. Inside the bubble, the Higgs field would have dropped to its true ground state, changing the masses of fundamental particles, altering the strength of forces, making atoms as we know them impossible. Chemistry would fail. Biology would fail. The stars would wink out. Galaxies would dissolve. And because this bubble expands at light speed, there would be no warning. You couldn't see it coming because light from the approaching boundary would arrive at the exact same instant as the boundary itself. Think about that for a moment. The light that would tell you about your impending doom would arrive at precisely the same instant as the doom itself. There's something almost merciful about that, isn't it? No anticipation, no dread, no watching the end approach. One moment you're here, the next you're simply not, along with everything else in the universe. The entire cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, countless planets, potentially other forms of life, all of human history, every work of art, every scientific discovery, every moment of joy and sorrow, every dream and hope, gone in an instant, erased so completely that it would be as if none of it had ever existed at all. This is the ultimate existential threat, one that makes asteroid impacts and supernovae look like minor inconveniences by comparison. But let's step back from the brink of oblivion for a moment and examine where this bizarre and terrifying idea actually comes from. The story of vacuum decay is really the story of our evolving understanding of what we mean by nothing. For most of human history, nothing meant nothing. The absence of things, empty space, void. But quantum mechanics, that strange and counterintuitive theory that governs the behavior of the very small, revealed that even nothing is something. Even in what we call a perfect vacuum, devoid of all matter and radiation, quantum fields persist, and these fields fluctuate, generating virtual particles that pop in and out of existence on timescales so brief they barely seem real. Yet these fluctuations have real, measurable effects on the world. They contribute to the Casimir effect. They influence the behavior of particles. They're woven into the very fabric of space-time itself. The concept of vacuum energy and vacuum states really came into focus in the mid-20th century as physicists grappled with quantum field theory, the framework that describes how quantum mechanics and special relativity work together. Every field, they realized, has a ground state, a lowest energy configuration, and the collection of all these ground states is what we call the vacuum. But here's where it gets interesting. A field might have more than one possible ground state, or what appears to be a ground state might not actually be the lowest energy state possible. This is where the idea of false vacuum comes in, and it was the brilliant physicist Sidney Coleman who really developed the mathematics of vacuum decay in the 1970s, showing how a field trapped in a false vacuum could tunnel through an energy barrier to reach a true vacuum. Sidney Coleman was one of those physicists whose name might not be widely known outside academic circles, but whose influence on theoretical physics is immeasurable. His work on vacuum decay, particularly his landmark 1977 paper, Fate of the False Vacuum, laid out with mathematical precision exactly how a false vacuum could decay through quantum tunneling, creating a bubble of true vacuum that would then expand at light speed. Coleman showed that if you're in a false vacuum, it's not a question of if it will decay, but when, and the when could be tomorrow, or it could be in a time span so vast it makes the current age of the universe look like an eye blink. The math was elegant, terrifying, and opened up entirely new ways of thinking about the stability of the universe itself. Now, you might be wondering, how do we actually know whether our universe is in a true vacuum or a false vacuum? This is where the story gets really fascinating because it involves one of the most important scientific discoveries of the 21st century. For decades, physicists had theorized about the existence of the Higgs field, a field that permeates all of space and gives particles their mass. The idea, proposed in the 1960s by Peter Higgs and several other physicists, was revolutionary. Particles don't inherently have mass, but rather they acquire mass by interacting with the Higgs field. The more a particle interacts with this field, the more mass it has. Photons, for instance, don't interact with the Higgs field at all, which is why they're massless and travel at light speed. Electrons interact with it slightly, quarks interact with it more, and so on. But the Higgs field was just a theory until physicists could detect its associated particle, the Higgs boson. This is a fundamental quirk of quantum field theory. Every field has an associated particle, and detecting that particle proves the field exists. The search for the Higgs boson became one of the great scientific quests of the modern era, requiring bigger and bigger particle accelerators to reach the energies needed to produce it. Finally, on July 4, 2012, scientists at CERN, the European Organization for Nuclear Research, announced that they had found it. Using the Large Hadron Collider, a circular tunnel 27 kilometers in circumference buried beneath the border of France and Switzerland, they had smashed protons together with such energy that Higgs bosons briefly flickered into existence before decaying into other particles. The discovery was monumental. confirming a crucial piece of the standard model of particle physics and earning Peter Higgs and François Englert the Nobel Prize in Physics in 2013. But here's where the celebration starts to feel a bit hollow, where the champagne starts to taste like ashes. The mass of the Higgs boson, which they measured to be about 125 gigaelectronvolts, combined with the mass of the top quark, tells us something troubling about the stability of our universe. You see, the shape of the Higgs field's potential energy, whether it's in a true vacuum or false vacuum, depends critically on these masses. If the Higgs boson had been lighter or heavier, or if the top quark had been different, we might live in a clearly stable universe or a clearly unstable one. Instead, we find ourselves in this twilight zone of metastability, where the Higgs field is probably in a false vacuum, but the barrier holding it there is high enough that decay is incredibly, almost impossibly unlikely on human timescales, but not impossible over cosmological timescales. Let me try to help you visualize this with a metaphor that might make it more concrete. Imagine you're placing a ball on a landscape of hills and valleys. If you place the ball in the deepest valley, it's in a true vacuum, a stable state where it has no tendency to move anywhere else. But now imagine there's a valley on the side of a mountain, a little dip where the ball can rest. It seems stable, and if you just glanced at it, you might think it was sitting in the lowest point available. But look further down the mountain, and there's a much deeper valley far below. Between where the ball sits and that lower valley, there's a hill, a barrier of higher ground. In classical physics, the ball would need enough energy to roll up and over that barrier before it could fall to the lower state. But quantum mechanics is stranger than classical physics. Quantum mechanics allows for something called tunneling, where a particle or field can, through sheer quantum randomness, appear on the other side of a barrier without actually having the energy to climb over it. Think of it like this. You're in a room with walls, and classically, you'd need to open a door or break through the wall to get out. But in the quantum world, there's a tiny, infinitesimally small probability that you could simply find yourself on the other side of the wall without ever passing through it. This happens with subatomic particles all the time. It's how radioactive decay works, how the sun fuses hydrogen into helium, how many electronic devices function. And it means that even if the Higgs field is sitting in a false vacuum, separated from the true vacuum by an enormous energy barrier, there's always a probability, however small, that somewhere in the vast expanse of the universe, a tiny region of that field will tunnel through to the true vacuum state. When that happens, when that first bubble of true vacuum forms, there's no going back. The true vacuum has lower energy than the false vacuum, which means the false vacuum region has excess energy, and that energy gets released as the bubble expands. This energy release drives the bubble wall outward at the speed of light. Inside the bubble, the physics is different. The Higgs field has a different value, which means particles have different masses, which means atoms don't form the same way, which means chemistry doesn't work, which means nothing we know can exist. The bubble is essentially a region of space with completely different physical laws, expanding inexorably, consuming the universe, rewriting reality as it goes. Now, here's a question for you to consider. If this is a possibility, if vacuum decay could happen at any moment, why hasn't it happened already? The universe is nearly 14 billion years old. That's 14 billion years of the Higgs field sitting in this metastable state, 14 billion years of countless quantum events, and yet we're still here. Does that mean we're lucky? Does it mean the probability is so low that even over cosmic timescales it's unlikely? Or does it mean something else entirely? Some physicists argue that the very fact we exist to ask this question is evidence that vacuum decay, if possible, must be extraordinarily rare. This is a kind of anthropic reasoning. We can only observe a universe in which vacuum decay hasn't yet occurred because if it had occurred, we wouldn't be here to observe anything. In the vast space of possible universes, or in an infinite multiverse scenario, we necessarily find ourselves in one of the branches where stability has persisted long enough for complexity, stars, planets, and life to emerge. But there's another possibility that's even more unsettling. What if vacuum decay has already started? What if, somewhere in the distant reaches of the observable universe, or perhaps even beyond what we can see, A bubble of true vacuum has already formed and is expanding toward us at light speed. Remember, we couldn't possibly know. The information that it was coming would travel at the speed of light, the same speed as the bubble itself, so we'd have no advance warning whatsoever. This very moment, a wall of oblivion could be racing toward you from across the cosmos, crossing billions of light-years of space, and you'd never know until the instant it arrived. It's a thought that makes even the most hardened physicist a little uncomfortable. Let me share with you some calculations that really put this in perspective, because the numbers involved are so extreme they're almost absurd. Physicists have estimated that if the universe is indeed in a false vacuum state, the typical timescale for vacuum decay through quantum tunneling is something like 10 to the power of several hundred years. To give you a sense of how incomprehensibly long that is, the current age of the universe is only about 10 to the power of 10 years, 14 billion or so. We're talking about a number with hundreds of zeros, a time span so vast that it makes the age of the universe look like a nanosecond by comparison. In practical terms, this means the probability of vacuum decay happening in the next second, the next year, the next trillion years, is so close to zero as to be effectively zero. By the time vacuum decay becomes likely, all the stars will have burned out, all the black holes will have evaporated through Hawking radiation, and the universe will be a cold, dark, empty expanse where nothing interesting happens anymore. So in one sense, vacuum decay is nothing to worry about. It's the least of our concerns compared to things like climate change or asteroid impacts that could actually affect us or our descendants. But, and this is a significant but, those calculations assume nothing accelerates the process. They assume the universe is just sitting there, quantum fields doing their quantum thing, occasionally producing random fluctuations. What if something could trigger vacuum decay? What if there were some high-energy event that could give the Higgs field the nudge it needs to tip over into the true vacuum? This is where the story takes an interesting turn, because when CERN was building the Large Hadron Collider, there was genuine public concern, even fear, that the high-energy collisions it would create might trigger exactly this kind of catastrophic vacuum decay. Picture the scene. It's the mid-2000s, and physicists are preparing to turn on the most powerful particle accelerator ever built, a machine that will smash protons together at energies never before achieved in a laboratory setting. The purpose is noble, the pursuit of knowledge, the search for the Higgs boson and other exotic particles that might reveal the universe's deepest secrets. But some physicists and many members of the public ask a simple question. Could these collisions create conditions that might destabilize the vacuum? Could we accidentally end the universe in our quest to understand it? The concern was serious enough that CERN commissioned safety reports, comprehensive reviews by panels of physicists examining whether the LHC posed any existential risks. The conclusion of these reports was reassuring. No, the LHC cannot destroy the universe. The reasoning goes like this. First, cosmic rays, high-energy particles from space, have been smashing into Earth's atmosphere and other celestial bodies at energies far exceeding what the LHC can produce for billions of years, and the universe is still here. If such collisions could trigger vacuum decay, it would have happened already somewhere in the cosmos. Second, even if the LHC could somehow produce conditions conducive to vacuum bubble formation, which seems extraordinarily unlikely, the calculations suggest that any bubble produced would be far too small and wouldn't have enough energy to expand. It would collapse back on itself almost immediately. Third, the probability of quantum tunneling to a true vacuum state is so staggeringly low that even directing all of humanity's energy resources toward making it happen wouldn't make a dent in the likelihood. We simply don't have the power to threaten the vacuum, even if we wanted to. These arguments are compelling and have satisfied most scientists and the public that the LHC is safe. But they rely on assumptions. Assumptions that we believe are true based on our current understanding of physics, but understanding that is, by necessity, incomplete. We don't have a complete theory of quantum gravity. We don't know what dark matter is made of. We don't fully understand dark energy or why the universe is accelerating in its expansion. There are gaps in our knowledge, and in those gaps, uncertainty lurks. Could there be some exotic mechanism we haven't thought of that might lower the barrier to vacuum decay? Could there be interactions between fields we haven't discovered that might make the vacuum more vulnerable than we think? Almost certainly not. But science deals in probabilities, not absolutes, and the probability, while vanishingly small, isn't quite zero. Now let's dive deeper into what the interior of a vacuum decay bubble would actually be like, because this is where physics gets truly alien. Inside the bubble, as the Higgs field settles into its true vacuum state, its value changes. Since the masses of particles depend on their interaction with the Higgs field, this means the masses of fundamental particles would be different inside the bubble. Electrons might become heavier or lighter. Quarks, the building blocks of protons and neutrons, might have completely different masses. The strength of fundamental forces, which also depend on the values of various quantum fields, might change. Electromagnetism might be stronger or weaker. The strong nuclear force that holds atomic nuclei together might not be strong enough to bind protons and neutrons, or it might be so strong that nuclear fusion happens spontaneously at all energies. The implications are staggering. Atoms as we know them probably couldn't exist. The delicate balance of forces that allows electrons to orbit nuclei in stable configurations, giving rise to the periodic table and all of chemistry, would be shattered. Even if some kind of matter could form inside the bubble, it would be unrecognizable, governed by entirely different rules. There would be no stars because the fusion processes that power stars depend on the current masses of particles and the current strengths of forces. There would be no planets, no chemistry, no complexity, no life. Just a soup of particles in configurations we can barely imagine. Physics so different from our own that we need new equations to describe it. Equations we couldn't possibly write because we no longer exist to write them. And then there's the bubble wall itself, the boundary between false vacuum and true vacuum, between our reality and the new one. The energy difference between the two vacuum states has to go somewhere, and it goes into the bubble wall, making it an incredibly energetic, violent boundary. As it sweeps through space at light speed, the wall would be like a cosmic scythe, utterly obliterating anything it encountered. The energy densities involved would be extreme, potentially higher than anything that exists in the current universe. Matter caught at the boundary wouldn't just be destroyed. It would be torn apart into its constituent particles, and those particles would be forced into new configurations as the physics around them changed. It would be a moment of absolute chaos, a nanosecond of pure physical violence as reality itself was rewritten, and then it would be over, leaving behind only the strange new physics of the true vacuum. Here's something that might make you uncomfortable. We have no guarantee that the true vacuum, if it exists, would even permit any form of structure or complexity. The anthropic principle tells us that we observe the universe with the properties it has because those properties allow for our existence. If the properties were dramatically different, we wouldn't be here to observe them. But the true vacuum has no such requirement. It doesn't need to support life or stars or galaxies or anything interesting at all. It could be a completely sterile state, an endpoint of physics where nothing but the simplest particles exist in isolation, forever. The false vacuum we inhabit, despite being unstable in the ultimate sense, might be the only state of the universe capable of supporting richness and complexity. If that's true, then vacuum decay isn't just the end of us. It's the end of meaning itself, the end of any universe that could be known or understood or appreciated. Think about that for a moment. Really let it sink in. The universe we know, with its billion trillion stars, its planets and nebulae and black holes, its four fundamental forces working in exquisite balance to allow for atoms and molecules and life. All of this might be a cosmic accident, a temporary bubble of false vacuum that happens to have the right properties to be interesting. And the true ground state, the state the universe wants to be in from an energy perspective, might be completely dead, devoid of any possibility for structure or awareness. It's a sobering thought, one that challenges our intuitions about the naturalness of our existence. We tend to think of the universe as being the way it is for a reason, that the laws of physics are what they are because they couldn't be otherwise. But vacuum decay reminds us that there might be other configurations, other possible universes with different laws, and we just happen to find ourselves in this particular one not because it's special in any deep sense, but because it's the only type that could contain observers asking the question. Let's shift gears for a moment and talk about the role vacuum decay plays in cosmology beyond just being a potential mechanism for the universe's demise. You see, physicists believe that vacuum decay might have actually happened in the early universe, multiple times, driving crucial transitions that shape the cosmos we inhabit. In the first fractions of a second after the Big Bang, the universe was unimaginably hot and dense, and at such energies, many quantum fields existed in different vacuum states than they do today. As the universe expanded and cooled, these fields underwent phase transitions, dropping from higher energy vacuum states to lower ones. One of the most important of these transitions is believed to have driven cosmic inflation, a period of exponential expansion that occurred when the universe was only a tiny fraction of a second old. The inflationary model, proposed by Alan Guth and others in the early 1980s, suggests that a field called the inflating field was trapped in a false vacuum state, and the energy of that false vacuum drove a period of incredibly rapid expansion, blowing the universe up from subatomic scales to macroscopic scales in an instant. When the inflating field finally decayed to its true vacuum, the energy released was converted into matter and radiation, essentially reheating the universe and setting the stage for everything that came after. In this view, vacuum decay isn't just a threat. It's a creative force, a mechanism by which the universe transitions from one state to another, sometimes producing the conditions necessary for structure and life. This raises a fascinating possibility. What if our entire observable universe is itself inside a bubble? What if the Big Bang wasn't the beginning of everything, but rather the moment when our local region of space transitioned from one vacuum state to another, creating the physics we observe while outside our bubble? Beyond the edge of the observable universe, completely different physics might apply. This is speculation, of course, but it's grounded in serious theoretical work. Some cosmological models propose a multiverse scenario where different bubbles with different vacuum states and different laws of physics nucleate and expand, occasionally colliding with one another. If such collisions occurred, they might leave imprints on the cosmic microwave background, the afterglow of the Big Bang, and physicists have actually looked for such signatures, though none have been definitively found. Imagine a cosmos filled with countless bubbles, each one a universe unto itself, each with its own laws determined by the vacuum states of its quantum fields. Some bubbles might have physics similar to ours, others radically different. Some might support complexity and life, others might be sterile and empty. These bubbles expand and occasionally collide, creating moments of cosmic drama on scales we can barely conceive. And each bubble might itself be metastable, capable of decaying into yet another state, creating bubbles within bubbles in an endless hierarchy of vacuum transitions. It's a dizzying vision, one that challenges the very notion of what we mean by the universe. But it's a vision that emerges naturally from our best theories of quantum fields and cosmology. Now, let's address a question you might be asking yourself. Is there any way to prevent vacuum decay? If we knew it was going to happen, could we stop it? The short answer is almost certainly no. Vacuum decay, if it occurs, is a fundamental process of quantum mechanics and field theory. It's not something you can shield against or redirect. It's not a physical object hurtling through space that you could destroy or deflect. It's a change in the underlying fabric of reality, and once it starts, it's governed by the laws of physics themselves. The bubble expands at light speed because the wall is a region of immense energy, and that energy drives the expansion. There's no mechanism within our current understanding of physics that could slow or stop such an expansion. But let's indulge in some speculation for a moment, keeping in mind that this is purely theoretical and ventures beyond established science. Could an incredibly advanced civilization, one with technology far beyond our current capabilities, potentially do anything about vacuum decay? Some physicists have mused about the idea of using enormous amounts of energy to stabilize the vacuum, perhaps creating some kind of field configuration that raises the barrier against tunneling. But the energies required would be astronomical, likely exceeding anything achievable even by a civilization that had harnessed the power of entire galaxies. And there's a catch, 22. The very act of manipulating fields at such high energies might itself trigger the vacuum decay you're trying to prevent, like trying to defuse a bomb with a sledgehammer. Another speculative idea involves the possibility of escaping into another universe before the bubble wall arrives. This ventures into the realm of wormholes and exotic space-time geometries, hypothetical structures allowed by general relativity but never observed and probably impossible to create or traverse. Even if you could create a wormhole to another universe, you'd face the problem that the other universe might have the same vacuum instability, or it might have physics so different that life as we know it couldn't survive there. And besides, the bubble expands at light speed, giving you no warning and no time to react. By the time you knew it was coming, it would already be upon you. So in any realistic sense, vacuum decay is not something that can be prevented, avoided, or survived. It's the ultimate existential threat, one against which no defense is possible. This brings us to a profound philosophical question. How should we feel about vacuum decay? Does the possibility that the universe could end at any instant make existence meaningless, or does it make each moment more precious? There's a philosophy concept called existentialism that grapples with the idea that existence precedes essence, that we're thrown into a universe without inherent meaning and must create meaning for ourselves. The possibility of vacuum decay takes this to an extreme, reminding us that not only our individual lives but the entire cosmos is contingent, temporary, ultimately fragile. Yet many people find this empowering rather than depressing. If nothing is guaranteed, if existence itself is a gift that could be revoked at any instant without warning, then perhaps the appropriate response is not despair but gratitude, a determination to make the most of the time we have, to find beauty and meaning and connection in the face of uncertainty. Consider this. Every person you've ever met, every sunset you've watched, every piece of music that moved you, every scientific discovery, every act of kindness, all of it exists against a backdrop of cosmic impermanence. The atoms in your body were forged in the hearts of dying stars billions of years ago, scattered into space, eventually coalescing into the sun and earth and you. You are, quite literally, stardust contemplating the cosmos, a way for the universe to know itself. And this has been true for nearly 14 billion years, through countless generations of stars and galaxies, through the slow development of complexity from simple atoms to molecules to life to consciousness. The fact that it could all end doesn't erase the fact that it happened, that it's happening now, that you're here to experience it. The value of existence doesn't depend on it lasting forever. It depends on the richness of experience while it lasts. But let's return to the science, because there are still many unanswered questions about vacuum decay, areas where current research is pushing the boundaries of our understanding. One major uncertainty involves the precise measurements of the Higgs boson mass and the top quark mass. Remember, these masses determine the shape of the Higgs potential and whether we're in a true vacuum, false vacuum, or right on the boundary. Current measurements place us in the metastable region, but there are still error bars on these measurements, ranges of uncertainty. Future, more precise measurements might shift our understanding, potentially revealing that we're actually in a stable vacuum after all, which would be enormously reassuring, or that we're even more metastable than we thought, which would be slightly less reassuring but wouldn't actually change much practically speaking given the timescales involved. Another area of active research involves looking for physics beyond the Standard Model. The Standard Model is our current best theory of particle physics, describing all known fundamental particles and 3 of the 4 fundamental forces. It's been incredibly successful, making predictions that have been verified to extraordinary precision. But we know it's not the final word. It doesn't include gravity. It doesn't explain dark matter or dark energy. It has various mathematical features that seem arbitrary or fine-tuned. Physicists expect that at higher energies, beyond what we can currently probe with particle accelerators, new physics must emerge, new particles and forces and fields that we haven't yet discovered. And these new fields could significantly affect the stability of the vacuum. For example, if there are additional particles that interact with the Higgs field, they could change the shape of the Higgs potential, potentially stabilizing it or destabilizing it further. Supersymmetry, a theoretical framework that proposes every known particle has a heavier supersymmetric partner, could stabilize the vacuum if the supersymmetric particles exist at certain masses. String theory, which attempts to describe all particles and forces as vibrations of tiny strings, introduces many additional fields and dimensions that could affect vacuum stability in complex ways. The problem is, we don't know which, if any, of these theories are correct, and without experimental evidence from higher energy scales, we're somewhat in the dark. This is one of the great frustrations of modern theoretical physics. We have brilliant mathematical frameworks that could extend our understanding beyond the standard model, but we lack the experimental data to determine which framework, if any, describes reality. The LHC was built partly in the hope of finding such evidence, signatures of supersymmetric particles or extra dimensions, or something unexpected that would point the way forward. So far, it's found the Higgs boson and little else beyond the standard model, which is both a triumph and a puzzle. Why does nature seem to respect the standard model so precisely up to the energies we can probe, only to presumably break it at higher energies we can't yet reach? It's a question that keeps physicists up at night. Let me share with you one of the more unsettling calculations related to vacuum decay, one that involves black holes. Stephen Hawking, the legendary theoretical physicist, showed in the 1970s that black holes aren't entirely black. Due to quantum effects near the event horizon, the point of no return around a black hole, they emit radiation, now called Hawking radiation, and very slowly evaporate over time. A stellar mass black hole would take vastly longer than the current age of the universe to evaporate, but smaller black holes evaporate faster, and a very tiny black hole would evaporate quickly in a burst of energy. Now, some physicists have calculated that if primordial black holes, tiny black holes that might have formed in the early universe, exist, and if they're evaporating, the final moments of their evaporation could release enough energy in a small enough volume to potentially trigger vacuum decay. The probability is still extremely low, but it's higher than the probability of spontaneous vacuum tunneling, which means evaporating black holes might be the most likely trigger for vacuum decay if it's going to happen. Does this mean black holes are ticking time bombs, each one a potential spark that could ignite the conflagration that ends the universe? Not really, for a couple of reasons. First, we're not even sure primordial black holes exist in significant numbers. They're hypothetical objects that might have formed from density fluctuations in the very early universe, but we've never definitively detected one. Second, even if they exist and are evaporating, the probability that any given evaporation event triggers vacuum decay is still astronomically low, so low that it wouldn't be expected to happen even once in the entire observable universe over the entire history of time we can meaningfully talk about. But it's a fascinating connection between quantum mechanics, general relativity, and the ultimate fate of the cosmos, a reminder that the universe is a deeply interconnected place where the behavior of the very large and the very small can have unexpected implications for one another. There's another twist to the vacuum decay story that's worth exploring, and it involves the expansion of the universe itself. Observations over the past few decades have revealed that the universe isn't just expanding, it's accelerating in its expansion. Galaxies are moving away from each other faster and faster over time, driven by something we call dark energy, a mysterious component that makes up about 68% of the universe's total energy density, but whose nature we don't understand. Dark energy acts like a kind of repulsive gravity, pushing space apart, and the leading candidate for what it might be is something called the cosmological constant, essentially a constant energy density inherent to the vacuum of space itself. But here's the connection to vacuum decay. If the cosmological constant is really a property of the vacuum, then the value we measure is the value associated with our current false vacuum state. If the universe were to decay to a true vacuum with a different cosmological constant, the expansion rate of the universe would change, potentially dramatically. Depending on the value of the cosmological constant in the true vacuum, the universe might start collapsing, crunching back down to a singularity, or it might expand even faster, tearing apart galaxies, stars, and eventually atoms in a scenario called the Big Rip. Or the cosmological constant might be zero in the true vacuum, which would mean the universe would expand at a constant rate determined only by its current motion, eventually leading to a cold, dark, diffuse state as all matter spreads out and energy dissipates. None of these scenarios are pleasant, but they add another layer to the already complex story of what vacuum decay might mean for the cosmos. Let's take a moment to address some common misconceptions about vacuum decay, because like many scientific concepts, it's easy to misunderstand or sensationalize. First, vacuum decay is not the same as the heat death of the universe. Heat death is the idea that the universe will eventually reach a state of maximum entropy, where all energy is evenly distributed and no useful work can be done. It's a slow, gradual process that would take an incomprehensibly long time, and it's based on the laws of thermodynamics. Vacuum decay, by contrast, is a sudden, catastrophic event driven by quantum mechanics and field theory. There are two different scenarios for how the universe might end, and they're not mutually exclusive. In fact, if the universe is metastable, heat death might set in long before vacuum decay ever occurs. Second, vacuum decay is not something humans could trigger, despite the fears that surrounded the LHC. We simply don't have the energy or the technology to significantly affect the stability of the vacuum. Even if we wanted to trigger vacuum decay, which would be the ultimate act of cosmic vandalism, we couldn't do it. The energies involved in determining vacuum stability are set by the fundamental constants of nature, things like the masses of particles and the strengths of forces, and these are many orders of magnitude beyond human capability to influence. Third, the possibility of vacuum decay doesn't mean we should live in fear or that existence is pointless. The probability of it happening on any timescale relevant to human concerns is vanishingly small, far smaller than the probability of countless other risks we face and largely ignore. You're infinitely more likely to be struck by lightning, win the lottery twice, or be hit by an asteroid than to be affected by vacuum decay in your lifetime or in the lifetime of human civilization. It's a theoretical possibility that tells us something deep about the nature of reality, but it's not a practical concern for daily life. Now, I want to take you on a journey into some of the more speculative ideas that physicists have considered related to vacuum decay, ideas that push the boundaries of current science and venture into the realm of informed speculation. Remember, these are not established facts, but rather thought experiments and theoretical musings that help us explore the implications of our current understanding. One such idea is the possibility of multiple metastable states, a kind of staircase of vacuum levels. Maybe the Higgs field isn't just in a false vacuum that could decay to a true vacuum. Maybe there's a whole sequence of lower and lower energy states, each one more stable than the last, but still not the absolute ground state. In this scenario, the universe could undergo a series of vacuum transitions, each one changing the laws of physics slightly, creating a sequence of different epochs with different rules. Imagine if this had happened in the past. Maybe the very early universe had very different physics, different particle masses, different force strengths, and through a series of vacuum decays, it transitioned through several states before settling into the current false vacuum we inhabit. Each transition would have been catastrophic, destroying whatever structures existed before and allowing new structures to form under the new physics. If we're in a metastable state now, maybe in the far, far future, the universe will undergo another transition, another reshuffling of the physical laws, and perhaps in that new state, new forms of complexity and even life might emerge, although they'd be so different from us that we couldn't recognize them as such. It's a cycle of cosmic death and rebirth, driven not by mysticism but by the quantum properties of fields. Another speculative idea involves using vacuum decay as a kind of ultimate weapon or tool in science fiction scenarios. If a civilization somehow gained the ability to trigger vacuum decay deliberately, they could theoretically use it to destroy not just planets or stars but entire regions of space, rewriting the laws of physics to suit their purposes. Of course, this is wildly beyond any plausible technology and faces the problem that you destroy yourself along with everything else since the bubble expands at light speed in all directions. But it's a staple of hard science fiction that explores the implications of physical theories, a reminder that our universe operates according to rules that allow for possibilities far stranger than most fiction dares to imagine. There's also been speculation about whether intelligent observers could exist in a universe undergoing vacuum decay. Could there be some form of life or consciousness that arises in the brief moment of the bubble wall's passage, or that exists in the strange physics of the true vacuum? This seems extraordinarily unlikely, bordering on impossible. The bubble wall is a region of intense energy and chaos, not conducive to any kind of stable structure, let alone the complex organization required for life. And the true vacuum, as we've discussed, might not permit any complexity at all. But the universe has surprised us before, And who's to say that consciousness necessarily requires atoms and chemistry as we know them? Maybe there are forms of information processing and awareness that could emerge from entirely different physical substrates, configurations of fields and particles that we can't imagine. It's almost certainly not the case, but it's a reminder that our intuitions about what's possible are shaped by our limited experience of one particular set of physical laws in one particular vacuum state. Let me share with you a thought experiment that really drives home the strangeness of vacuum decay. Suppose, hypothetically, that scientists tomorrow announced they had detected a bubble of true vacuum somewhere in a distant galaxy, expanding toward us at light speed. They can see it because its approach has distorted the light from galaxies behind it, creating a characteristic signature. They calculate that it will reach Earth in, say, 1 million years. What would happen? How would humanity react to the knowledge that the universe, as we know it, has a definite expiration date, and not even a particularly long one on cosmic scales? 1 million years might seem like a long time, and in human terms, it is. It's 20 times longer than modern humans have existed as a species. It's long enough for evolution to shape us into something potentially unrecognizable, long enough for civilizations to rise and fall countless times, long enough to colonize the galaxy if we develop the technology. But it's also a finite deadline, a cosmic clock ticking down to oblivion. You can't escape it by fleeing because the bubble expands at light speed, filling the entire universe eventually. You can't stop it or redirect it. All you can do is watch it approach and know that everything ends when it arrives. Would such knowledge change how civilization develops? Would we become more hedonistic, focused on pleasure and experience in the time remaining? Or more purposeful, determined to create and discover and explore as much as possible before the end? Would we unite as a species in the face of ultimate doom, or would we fragment and despair? Would we spend the time trying to find a way to survive, perhaps uploading consciousness into some exotic form that might persist through the transition, even though physics says it's impossible? It's a fascinating question about human nature and values, about what we consider meaningful when ultimate meaning is foreclosed. Of course, this scenario is entirely hypothetical. We haven't detected any such bubble, and if one existed anywhere in the observable universe, we'd have no way to see it coming, remember, because it moves at light speed. But the thought experiment reveals something about our relationship to existence and finitude. We're all living under a personal deadline. None of us will survive more than a century or so, and yet most of us find ways to create meaning and purpose despite that. Maybe a civilization facing cosmic doom would do the same, scaling up the very human process of finding significance in the temporary, beauty in the ephemeral. Let's turn our attention now to some of the cutting-edge research being done on vacuum stability, because this is an active area of theoretical and experimental physics. At CERN and other particle physics laboratories around the world, scientists are working to make ever more precise measurements of the Higgs boson and top quark masses, because these measurements directly inform our calculations of vacuum stability. Every decimal place of precision matters, potentially shifting our estimates from clearly metastable to possibly stable or vice versa. It's painstaking work, requiring enormous detectors, sophisticated analysis, and years of data collection. But it's how we refine our understanding of the universe's fundamental properties. Theorists, meanwhile, are exploring the mathematical structure of quantum field theory itself, looking for better ways to calculate the effective potential of the Higgs field. These calculations are extraordinarily complex, involving quantum corrections and loop diagrams and renormalization procedures that push the boundaries of our computational capabilities. Small changes in how these calculations are performed can lead to different predictions about vacuum stability, which is why cross-checking and improving the mathematical methods is crucial. Some physicists are also investigating whether there might be additional fields or interactions beyond the standard model that could affect the Higgs potential in ways we haven't accounted for. There's also fascinating work being done at the intersection of quantum field theory and cosmology, looking at how vacuum stability might be affected by the conditions in the early universe. When the universe was very young, very hot, and very dense, quantum fields existed in a thermal bath of particles and radiation, and this can affect their effective masses and interactions. Some calculations suggest that the Higgs field might have been more stable in the early universe than it is now, or less stable, depending on the details. Understanding this could help us determine whether we need to invoke new physics to explain why the universe made it through those early epochs without undergoing vacuum decay. It's a puzzle that connects the smallest scales of particle physics to the largest scales of cosmology, the kind of interdisciplinary challenge that modern physics thrives on. One particularly intriguing question is whether the process of inflation, that period of exponential expansion in the early universe, might have involved vacuum decay events. If the inflating field, the field that drove inflation, was itself in a false vacuum, then its decay would have released enormous energy, reheating the universe and creating all the matter and radiation we see today. This is actually a standard feature of many inflationary models. Inflation ends through a kind of controlled vacuum decay, a transition from the high-energy false vacuum that drove the expansion to a lower energy state that allowed for normal physics. If this is what happened, then we've already lived through at least one vacuum decay event, or rather, the universe lived through it before we existed, and it was that event that set the stage for everything that came after. It's a reminder that vacuum decay isn't always destructive. In the right circumstances, it can be creative, a mechanism for phase transitions that allow the universe to evolve and change. This brings up a deep question. Is the universe as we observe it fine-tuned for our existence, or are we just lucky? The values of fundamental constants like the masses of particles and the strengths of forces seem remarkably well suited to allow for the existence of stars, planets, and life. Change any of them by even a small amount, and the universe would be a very different, likely sterile place. Some people take this as evidence of design, an argument that the universe was created with us in mind. Others invoke the multiverse, the idea that there are countless universes with different values of these constants, and we necessarily find ourselves in one of the rare ones where life is possible because we couldn't exist in the others. The vacuum stability question fits into this debate. If we're in a metastable vacuum, is that an accident, or is there some deeper reason? The anthropic principle suggests that we shouldn't be surprised to find ourselves in a universe with properties that allow for observers, even if those properties are improbable, because in universes where observers can't exist, there's no one to notice. This can feel like circular reasoning, but it's actually a legitimate constraint when thinking about cosmology and fundamental physics. If the universe could settle into many different vacuum states, each with different physical laws, then the fact that we observe laws compatible with complex chemistry and life tells us something. It tells us we're in one of the branches of the multiverse, or one of the epochs of cosmic history, where such laws apply. It doesn't tell us why those laws exist in the first place, but it does explain why we're experiencing them rather than some other set. Let me paint a picture for you of what the universe might look like in the far future, assuming vacuum decay doesn't occur. Fast forward trillions of years from now. All the stars have burned out, fusing all available hydrogen into heavier elements and then exhausting their fuel. Some have collapsed into white dwarfs, slowly cooling over eons. Others have exploded as supernovae, leaving behind neutron stars or black holes. The universe has expanded so much that galaxies are isolated from one another, each alone in an ever-growing void. Eventually, even protons might decay, if certain grand unified theories are correct, dissolving all remaining matter into radiation. Black holes evaporate through Hawking radiation, taking vast stretches of time to do so, but eventually even they vanish in a final whisper of particles. What's left is a dark, cold, empty expanse, close to absolute zero in temperature, with only the faintest quantum fluctuations disturbing the void. This is the heat death, the endpoint of thermodynamics, a universe in maximum entropy where nothing interesting can ever happen again. In that far future, after all the black holes have evaporated and all the matter has decayed, vacuum decay might become the universe's final chapter. With no energy sources, no structure, nothing but empty space and quantum fields, the probability of vacuum tunneling would continue to tick along, infinitesimally small but never quite zero. Given enough time, truly cosmic spans of time that dwarf the current age of the universe like the universe's age dwarfs a human lifetime, eventually, quantum fluctuations might nucleate that first bubble of true vacuum. And it would expand, consuming the empty void, changing the properties of the vacuum itself, and transitioning the universe into its final, ultimate state. There would be no one to observe it, no one to care, but it would be the last thing that happens, the final punctuation mark on the story of existence. It's a bleak vision, admittedly, but there's something almost poetic about it as well. The universe begins in a hot, dense state, filled with energy and potential. It expands and cools, allowing for the formation of structure, stars, galaxies, planets, life, consciousness. It reaches a peak of complexity and then slowly winds down as entropy increases and usable energy dissipates. Eventually, it fades into darkness and silence, and then, in one final quantum event, it transitions to a new state, closing the book on this particular chapter of cosmic history. It's the universe's way of moving from one configuration to another, indifferent to our hopes and dreams, following the impersonal laws of physics to their ultimate conclusion. But let's not end on quite such a somber note. Remember, all of this is based on our current understanding of physics, an understanding that, while impressive, is certainly incomplete. We've been surprised before, and will be surprised again. 100 years ago, we didn't know about quantum mechanics or general relativity, didn't know the universe was expanding, didn't know about nuclear fusion or black holes or the cosmic microwave background. 50 years ago, we didn't know about dark energy or the acceleration of the universe's expansion. 20 years ago, we hadn't found the Higgs boson or detected gravitational waves. Each generation of physicists has uncovered new phenomena, new principles, new layers of reality that previous generations couldn't have imagined. It's entirely possible, perhaps even likely, that future discoveries will change our understanding of vacuum stability. Maybe there are new fields or new interactions that stabilize the vacuum in ways we haven't considered. Maybe the true vacuum, if it exists, isn't as inhospitable as we think. Maybe there are aspects of quantum gravity, the long-sought theory that unifies quantum mechanics and general relativity, that change the picture entirely. We're working with the best tools we have, but those tools have limitations, and we should remain humble about the scope of our knowledge. Consider this question: what would it take for you to fundamentally change your worldview? What discovery, what piece of evidence, would shake your basic assumptions about reality? For many people, the answer is that they don't know, they've never really thought about it, because the world seems solid and reliable and unchanging on a day-to-day basis. But science is built on the willingness to revise beliefs in light of new evidence, to follow the data wherever it leads, even if it leads to uncomfortable conclusions. The possibility of vacuum decay is one of those uncomfortable conclusions, emerging from our best theories and our most careful measurements, but it's held tentatively, subject to revision as we learn more. There's a concept in philosophy called epistemic humility, the recognition that our knowledge is limited and provisional, that we might be wrong about things we feel certain about, and that overconfidence in our understanding can blind us to new possibilities. Science embodies this principle, at least in theory, constantly testing and questioning and refining. The story of vacuum decay is still being written. Each new measurement, each new theoretical insight, adds a paragraph or revises a sentence. We don't yet know the ending, whether the universe is stable or metastable or delicately balanced on the edge. We're detectives examining clues, trying to piece together the nature of reality from indirect evidence. And it's slow, difficult work. Let me bring this back to something more immediate, more personal. You might be wondering why any of this matters to you, living your life here on Earth, worrying about everyday concerns like work and relationships and paying bills. The universe's ultimate fate seems distant, abstract, irrelevant to the texture of daily experience. And in a practical sense, you're right. Vacuum decay, if it's even possible, won't affect your life or the lives of your descendants for countless generations. But I'd argue that understanding our place in the cosmos, grappling with these deep questions about existence and impermanence, does matter in a different way. It provides perspective, a sense of scale, a reminder that we're part of something much larger than ourselves. When you look up at the night sky, you're seeing light that left distant stars years, centuries, or even millennia ago. You're looking back in time, seeing the universe as it was, not as it is now. Those photons have traveled across the void, carrying information about the stars that emitted them, and they end their journey by striking the retina in your eye, creating a cascade of chemical and electrical signals that your brain interprets as vision. In that moment, you're connected to the cosmos in a very real, physical way. The iron in your blood, the calcium in your bones, the carbon in your cells, all of it was created in the nuclear furnaces of stars long dead, scattered into space when those stars exploded, eventually coalescing into the solar system and Earth and you. You are literally made of star stuff, and thinking about vacuum decay, thinking about the fundamental nature of reality and its potential fragility, is part of the ongoing human project of understanding where we come from and where we're going. There's also something profound about confronting the possibility of endings, of finitude, whether personal or cosmic. It can make the present moment feel more vivid, more significant. If everything could end at any instant, then right now is all we have, and that makes now infinitely valuable. This isn't an argument for recklessness or nihilism, but rather for engagement, for presence, for appreciating the improbable gift of existence while it lasts. The atoms that make up your body will outlast you, recycling into the environment, eventually becoming part of other structures, other beings. But the particular configuration that is you, the pattern of information and experience that constitutes your consciousness, is temporary, and that temporariness is what makes it precious. The same might be true for the universe itself. If it's metastable, if it's ultimately temporary, does that diminish its grandeur? Does it make the galaxies less beautiful, the laws of physics less elegant, the emergence of life less miraculous? I don't think so. If anything, it enhances these things, imbuing them with poignancy, the bittersweet awareness that all of this is contingent, not guaranteed, existing against a backdrop of quantum uncertainty. The universe doesn't owe us stability or permanence. The fact that we're here at all, that complexity and consciousness have emerged from simple ingredients and simple rules, is extraordinary, regardless of whether it lasts forever or only for a very, very long time. Let's consider one final speculative scenario, a thought experiment that pushes the boundaries of physics and philosophy. Suppose that consciousness or information is somehow more fundamental than we realize. Suppose that the pattern of information that constitutes a mind could, in principle, be encoded in different physical substrates, not just biological neurons but potentially in quantum fields themselves. This is wildly speculative, bordering on mystical, and there's no evidence for it, but bear with me. If information is fundamental in some deep sense, if the universe is at its core a process of information exchange and transformation, then maybe some echo of what existed could persist through a vacuum decay event, encoded in the new physics of the true vacuum. This idea connects to some interpretations of quantum mechanics, particularly those that emphasize the role of information and observation in collapsing wave functions and determining outcomes. It also relates to theoretical work on black hole information paradoxes and holographic principles, ideas suggesting that information is never truly destroyed, only transformed. If this is true at a fundamental level, if the universe conserves information in some sense, then maybe vacuum decay isn't total annihilation but rather transformation, a reshuffling of information into new patterns governed by new rules. Maybe, in some sense we can't currently comprehend, something of this universe would carry forward into the next state. Am I saying I believe this? No, not really. There's no evidence for it, and it contradicts our current understanding of what would happen in vacuum decay. But it's an example of how far you can push these ideas when you start asking deep questions about reality, information, and existence. Science progresses by entertaining wild possibilities and then figuring out how to test them, eliminating the ones that don't match observations and refining the ones that do. Most wild ideas turn out to be wrong, but occasionally, one turns out to be right, revolutionizing our understanding. The history of science is littered with concepts that seemed absurd when first proposed. Atoms, germs, continental drift, black holes, quantum entanglement, dark energy. Each one was met with skepticism, each one required extraordinary evidence, and each one eventually became part of our accepted understanding of the world. So where does this leave us? We've journeyed through the concept of vacuum decay, from its origins in quantum field theory to its implications for the universe's fate. We've explored the role of the Higgs field, the measurements that suggest we live in a metastable universe, the terrifying beauty of a bubble of true vacuum expanding at light speed, rewriting the laws of physics as it goes. We've considered the timescales involved, so vast that vacuum decay is more likely to happen after the stars have all burned out than any time soon. We've looked at connections to cosmology, to the early universe, to the possibility of multiverses and eternal inflation. We've grappled with the philosophical implications of cosmic impermanence and the question of meaning in a finite universe. The truth is, we don't know for certain whether our universe is stable or metastable. The measurements are tantalizing, placing us right on the edge, but there are still uncertainties, still error bars that could shift the conclusion one way or the other. And even if we are in a false vacuum, the probability of decay on any human-relevant timescale is so infinitesimally small that it's not something to lose sleep over. You're safe. Your descendants are safe. Humanity, if it survives the challenges we face, could persist for millions or billions of years without vacuum decay being a concern. But the possibility is there, lurking in the mathematics, a reminder that the universe operates according to rules that permit endings, transformations, fundamental changes in the nature of reality itself. And perhaps that's the real takeaway from all this. The universe is stranger, more wonderful, more precariously balanced than our everyday experience suggests. We live in an era where we can probe the fundamental structure of reality, where we can ask questions about the ultimate fate of existence and make at least tentative answers based on rigorous mathematics and experimental data. We can contemplate scenarios like vacuum decay not as idle speculation but as genuine possibilities grounded in our best understanding of how nature works. That's an incredible privilege, a testament to centuries of scientific progress, to the accumulated efforts of countless researchers pursuing knowledge for its own sake. Think about the scientists working at CERN, smashing particles together, sifting through data for signals that might reveal new physics. Think about the theorists filling blackboards with equations, trying to calculate the shape of the Higgs potential to one more decimal place of precision. Think about the cosmologists studying the cosmic microwave background, looking for clues about the early universe that might inform our understanding of vacuum stability. These people are driven by curiosity, by a desire to understand, by the same impulse that makes you wonder about the stars or ponder the nature of time or ask why anything exists at all. They're asking the universe questions, and sometimes, if they ask carefully enough and listen closely enough, the universe answers. So the next time you look up at the night sky, when you see those distant points of light scattered across the darkness, remember that each one is a sun, a massive nuclear furnace fusing elements and pouring energy into the void. Remember that the space between them, that seemingly empty blackness, is actually filled with quantum fields humming with energy, fields that determine the properties of matter and the possibilities for existence. Remember that there's a chance, vanishingly small but not zero, that somewhere in that vast expanse, a bubble of different physics could be forming, expanding, transforming reality as it grows. And remember that despite all this, despite the uncertainties and the cosmic threats and the ultimate impermanence of everything, we're here now, conscious and aware, able to contemplate these mysteries, and that's something worth marveling at. The universe could end in an instant. Vacuum decay could happen. The laws of physics could change. Everything we know could vanish faster than thought, leaving no trace that it ever existed. But it probably won't, not anytime soon, not in any time frame that matters to us or our descendants or the future of consciousness in this cosmos. And in the meantime, we have this moment, this configuration of particles and fields that allows for planets and people and wondering about our place in it all. We have the ability to ask questions that reach to the very foundations of existence, to peer into the mathematics that governs reality and glimpse possibilities both terrifying and sublime. We have each other, fellow travelers on this improbable journey through space-time, sharing this brief window of awareness between the Big Bang and whatever comes next. The story of vacuum decay is ultimately a story about the nature of reality itself, about stability and change, about permanence and impermanence, about the delicate balance of forces and fields that makes existence possible. It's a reminder that nothing is guaranteed, that the universe doesn't owe us anything, that the fact we're here at all is extraordinary. It challenges us to think deeply about what we value, what we consider meaningful, how we respond to uncertainty and the possibility of endings. And it showcases the power of human reason and creativity, our ability to take abstract mathematics and careful measurements and use them to deduce profound truths about the cosmos. So could the universe end in an instant? Yes, according to our best current understanding, it could. Will it? Probably not, at least not any time in the imaginable future. Should you worry about it? No, not in any practical sense. But should you think about it, ponder its implications, let it expand your perspective on existence and time and the nature of reality? Absolutely. Because these questions, these deep inquiries into the fundamental structure of the cosmos, are part of what makes us human. They're part of our ongoing conversation with the universe, a conversation that began when our ancestors first looked up at the stars and wondered what they were, and that continues today in laboratories and observatories and universities around the world. The universe is vast and ancient and filled with mysteries we're only beginning to unravel. Vacuum decay is one of those mysteries, a possibility that emerges from the equations of quantum field theory and the measurements of particle masses, a scenario that seems like science fiction but is actually grounded in our best science. Whether it will ever happen, whether we'll ever know for certain if we're in a true vacuum or a false one, whether the universe is ultimately stable or merely metastable, these questions remain open. The research continues. The measurements get more precise. The theories get more refined. And slowly, incrementally, we edge closer to understanding the true nature of the reality we inhabit. In the end, perhaps the most important thing is not the answer but the asking, not the destination but the journey. We're explorers in the truest sense, pushing at the boundaries of knowledge, venturing into conceptual territories no one has mapped before. We're trying to understand where we came from, how we got here, and where we might be going. We're seeking patterns in the chaos, meaning in the mathematics, connection across the vast gulfs of space and time. And in that seeking, in that striving to comprehend, we find something profoundly human and profoundly valuable. The universe could end in an instant, consumed by a bubble of true vacuum, all the laws of physics rewritten, everything we know erased without warning or trace. But right now, in this moment, it hasn't. Right now, the stars are shining, the galaxies are turning, the quantum fields are humming with their characteristic energies, and you're here, aware, thinking, wondering. Right now, the universe exists in this particular configuration, this particular set of vacuum states, this particular expression of physical law that allows for complexity in consciousness and the asking of deep questions. And that's extraordinary. That's worth appreciating. That's worth protecting and celebrating and exploring for as long as we can. So yes, the universe could end in an instant, but it also might not. It might persist for timescales that make eternity seem brief. It might be stable after all, or if it's metastable, the decay might be so far in the future that it's effectively never. We don't know yet, and that uncertainty is part of the adventure. We're figuring it out, piece by piece, measurement by measurement, insight by insight. And in the meantime, we have this moment, this precious, improbable, beautiful moment of existence, and that's more than enough.